Okay, questions? All right, let's also discuss how operators can be expanded in this formalism. We'll just, okay, so in terms of planning, we'll probably finish most of formalism today, discussion of the formalism today. You may have some left for Monday also, but after that we start the three-dimensional systems, okay, and we'll just look at separation of variables a little bit, but then move on to angular momentum, because the most important thing that comes up with going into 3 dimensions is the introduction of the angular momentum, which has a aesthetically very nice, very beautiful theory, which we'll discuss, and then we'll look at spin, etc., and finally the hydrogen atom. Okay, so let's just look at how we can represent operators in this formalism. So we have this operator A, which operates on this object psi and gives us another state vector. Okay, so that's what operators do. Okay, they take a state vector, operate on it, and give you something else. But one thing you can do is you can just put in identity operators, okay, to the beginning and the end of the operator in any basis that you like. Okay, so suppose I choose a certain basis. Let's choose the basis of the Hamiltonian. Okay, it doesn't have to be the Hamiltonian, but the Hamiltonian eigenstates look like this. Okay, and let me insert identity operators to the beginning and end of this. So what do I get? I'm going to get sum over I and j, because there are 2 identity operators. Over here, I am putting in ui. Okay, so that's an identity operator. A, and then uj. Okay, so this piece here is just the A operator, right? Identity on the left, identity on the right. Okay, this will operate on some psi, which means I'll take an inner product of these things, and that will give me a phi. But now look at the structure of this operator. Okay, I have this ui and uj on the left and the right, but what I have in the center is just a number. Okay, so this object here, which is the inner product, okay, from the left and right with ui and uj, I'm going to call it aij. Okay, so this is called the matrix element, okay, ij, of operator A, okay, in basis of ui. So it will be different if you choose a different basis, obviously, because there's an infinitely many ways of obviously choosing this orthonormal basis. Okay, I can choose UJs, I can choose eigenvectors of some other operator. Okay, but when I do that, I get this Aij, which is a number. Okay, now this is called the matrix element. Okay, so let's see why doing something like that may be useful. Okay. So let's see. So for one thing, let's see what something like that. Okay, so let me say, just consider A times B. Suppose I have two operators, A and B. Now, what happens to the matrix representation? Let's just expand that. So what am I going to do? I'm going to insert an identity operator here, an identity operator in between, and an identity operator out here. Okay? So AB is going to be equal to three identity operators. So there will be, okay, three summation terms, I, J, K. Let me start with the I operator, UI, UI, okay. Then A, UJ, UJ, it's the second identity operator. And then finally B, UK, UK. Okay, so that's my operator. But these things are now just matrix elements. This is Aij, and this is Bjk. So what does the matrix representation of this A times B correspond to? Well, it corresponds to Ijk. Okay, UI, U, A, I, J, A, B, J, K, okay, UK. So it's just like the matrix representation for A. Okay, I have this UI and UK at the end, which makes it an operator, right? Okay, so anything which looks like this is an operator because it operates on something to the right. So if I have a psi on the right, for example, a ket, it will give me an inner product here, and itself will result in a set of kets. So it will take a ket and give me a ket. Okay, so that's why it's an operator. Okay, so now looking over here, you see this object here, something summed over this middle index is what we do in matrix multiplication, right? So this is really, let me leave just the first and the last indices, I and K. So I'm going to get UI, the matrix product, okay, or operator product, doesn't matter, I, K times UK. Okay, so these matrix elements interact with one another as if, okay, they are matrices. That's why we call them matrix elements. Yes.
I couldn't understand that. How did we relate Aij with an element of the matrix? I couldn't understand.
Okay, well, it's mainly a definition. I have an operator. I take an inner product of this from the left with ui and from the right with uj, and I call it the matrix element. Okay. Now, does this have any relation to matrices that we know? Well, they seem to follow the matrix product rule. Okay, so the I-kth element of AB is Aij Bjk summed over the inner index J. Okay, so this is just matrix product. So it obeys the matrix product. Let's also look at the Hermitian properties related to hermiticity. If I have, for example, two states, okay, so let's look at, well, maybe I'll just keep on to, okay, so if I have ui, a uj, okay, then I know from the definition of the Hermitian adjoint that this is equal to A operating towards the left, so A dagger, Hermitian adjoint, operating on ui, and uj is on the left, complex conjugate, right? Okay, so what do I get? I get Aij is equal to A adjoint Ji complex conjugate. Okay, so this is how hermiticity in matrices is defined, and we also get that. Okay, so these things operate as if they are matrices. Okay. Now, let's look at a special case. Okay, let's look at the matrix representation of the Hamiltonian H. Okay. Now, how do I look at that? Well, H is going to be equal to, again, two identity operators, I and J. So ui, uj, I'm sorry, ui again. This is the first identity, H, and then uj, uj. Okay, so this is my Hij. But since these u's are eigenstates of H, okay, I know that H times uj, for example, is equal to energy of the jth state times uj. Right? So I can take out an Ej here, and I am going to get, okay, delta Ij ui, and I'm going to get Ej, but inner product of ui with uj, uj. And this thing, inner product of these states, we know are orthonormal. So that's going to give me a delta Ij. So I can remove one of the summations. And I'm going to get ui, okay, Ej delta Ij, uj, well, okay, I took care of that, so this is Ei, ui, okay, I. So this object here is, right, Ej times delta Ij is the matrix elements of H. So what does the matrix for H look like?
It's diagonal.
Okay, it's diagonal because I have zeros unless I is equal to j. So let's just put that matrix over here. Okay, so H is going to look like, okay, so entry 1, 1 here is going to be E1, but all zeros, okay. For the second element, I'll get E2 and zeros, okay, E3, zeros, okay, so these are the I elements, these are the J elements. So I get zeros unless I is equal to J, and this is what my Hamiltonian looks like in its own basis. Any operator actually will be diagonal in its own basis, right? If I had the operator A here and I expanded it in terms of the A basis, okay, it would be diagonal. So any operator is diagonal in its own basis, but for the Hamiltonian I have something like this, so it's an infinite by infinite matrix, and that's what I get. Okay, now you see there is a interesting application of these things. You can okay, so sometimes you have a system, even the system that we studied, the particle in a box system, if you have a sufficiently deep potential, okay, deep and abrupt potential like this, you see what type of energy levels you get. You get an E1, which has some value. Okay, it was what, h bar squared k, which is pi squared over a squared, right? And there's a 2m. Okay, so that's the energy of the ground state of this system. The next state is E2, which is, okay, you have an n squared coming in, so it's 4 times E1. Now the next state is really much higher. Okay, so E3 is 9 times E1. Now sometimes you have a physical problem in which you don't have that many energetic events around, okay, and the particle is in here and it's in contact with its environment. But the energy level, okay, of the interactions of this thing with its outside is quite low. Okay, so if you shine a laser light, perhaps you shine a laser light with this energy, etc. So this third energy level is just too high up. Okay, and you say, well, let me just ignore this part of the problem, because that involves too high an energy, and it's very unlikely that the particle will go up to that energy levels. Okay, so let me ignore that. Or you could keep 3 of them and ignore the 4th one. Okay, doesn't matter. Then in that case, you see, what you are doing is, in this expansion, you are ignoring, you are approximating this Hamiltonian with a Hamiltonian which has just 2 energy states. Then what happens? You get an H, okay, a better handwriting, H, which will be equal to, okay, I, well, I don't even need the summation, I have just 2 terms, okay, so I'm going to have U1, E1 plus U2, E2. Okay, this is obviously an approximation, but that's your Hamiltonian. Okay, so this is now, you would call this a 2-state system. So the system is not really a 2-level system, but what is interesting to you, okay, the dynamics that are interesting to you happens only with these 2 energy levels. So you don't have to consider the full Hamiltonian. All you need to do is consider just this piece. Okay? So if you want to write it like a matrix, it looks like E1, 0, 0, E2. So that's my H. Simple as that. Okay?
So this
Yes.
is not operator, right? The matrix.
Well, okay, this is the matrix representation of H.
Okay, so it is not the operator.
No, operator is here.
Okay.
Okay, operator is this thing here. Okay, so but in the matrix representation, this becomes an H. Okay, so we have now very many representations in which we can write this H. The original H is the H that we studied, okay, with p squared over 2m and v of x, etc. Okay, so this is in the Hilbert space representation of H, and this is the matrix representation of H. So you can use any one of them. Yes.
You can also write the operator of A's by using methods representation by the second equation, right? There.
Which second equation? This one?
Yeah, above that one.
Well, yes, okay, it's the same as this one, right? It's the same as this. Okay, so in fact, if you went to the seminar yesterday, I don't know if any of you were present. Did any of you go to the seminar yesterday? Anyway, okay, just a few. Okay, there was a lot of discussion about the two-state system, okay, all the time. So the two-state system that they are describing is something like this. It doesn't mean that it doesn't have a third or fourth, etc. But for their interest, it looks like a two-state system. Okay, so if you are working with a two-state system, this is the system that you work with. Okay, now you might say, why is this so interesting? It's just a diagonal matrix, but this is the simplest case corresponding to the particle in a box. But now suppose you put in some process through which you send particles from one state to the other. They will appear as off-diagonal terms that enter into this H, and then you have to find its eigenvalues again, because now you have modified H into something else, and then you have to work with that. Okay, so this is quite common in many applications. You use two-level systems. Yes.
Can you explain again why do we exclude E3?
Because it's a good approximation. Okay, so it will turn out that if I am working with only low energy events here, then this energy level way up here is not going to be relevant. You will eventually, expect that to happen because this is just going up faster and faster, right? So En is equal to n squared times E1. So if you go to something like n equal to 50, quite obviously there's a very large energy, and at that energy, probably the model breaks down. It's not going to be valid. So when we are discussing systems like this, we always assume that the particles are really at the lower energy states, and that's what we work with. Yes.
How we can quantify what is the error for this approximation?
How we can quantify it? Well, the best way of quantifying it is include the E3, do your calculations again, and see if there's a difference. Okay, so in many approximations, even numerical approximations, if you want to test the accuracy of your approximation, you just go one order higher, do the calculation again, see if you get a different result. Okay, and that will give you. Okay. All right. How are we doing on time? Okay, we are good. Okay, let me move to a slightly different topic, which will be yes.
Should we always diagonalize the Hamiltonian when we're working with it in matrix representation?
No, you can use matrix elements in any representation you like. Again, the best representation to work with is the representation which makes your life easier. Okay. Let's see. Well, we could also discuss how we can go from one representation to another, but perhaps that's too technical a detail. Let's see. Excuse me. Let's see. Okay, so let's look at function of an operator. Excuse me. Okay. So we will define the function of an operator in the same way as we define function of a variable. So, for example, if I have a function f of x, which is defined by a Taylor expansion, okay, if I have something like this, okay, then I define the function of same function of some operator A through the same series. Okay, so this goes from 0 to infinity. Okay, so here x to the 0 is 1. Here a to the 0 is the identity operator. Okay, same operator. Okay, for example, if we have n x to n over n factorial equal to e to the x, right? This is how e to the x is defined. Similarly, e to the some operator a is defined as identity plus operator a plus 1 over 2 factorial a squared plus 1 over 3 factorial a cubed, etc. Okay, so I have something like this. Sure.
What do we mean by the square of the nth power of operator?
Okay, a squared is just a times a. Okay, similarly, for example, we had p squared in the energy, right?
Of course, but
So a to the n is just n operators multiplied by one another.
so, for example, what do you mean? Yeah, of course, by the Taylor says we can create the a power a. But what is the meaning of this?
Okay, it's useful. Just wait. Okay, it's useful. Okay, so I have something like this. All right, so one thing, obviously you see function of an operator is an operator itself. So it's going to operate on stuff. Okay, now what happens, for example, when I have some function of an operator operating on a state vector, okay, on some psi? Well, this is going to be obviously complicated. This means that these are just going to multiply them one way or another. But we can make our life a little easier by inserting an identity here. You see, there are not that many bright ideas in physics. You just do the same thing again and again. Okay, let's insert this identity in between. And I'm going to get, okay, something which looks like, okay, and I'm going to insert, okay, let's see. Too many series. Let me just put f of a first. F of a. Okay, and here I have some I. Let me expand it in terms of the eigenstates of the operator A. Okay. So what will that be equal to? Well, I have the expansion over here. So it's going to be, in terms of f of a, I am going to get n from 0 to infinity, a to the n, right, operating on this thing, ai, psi. Now, this is n operations of this vector A, right, on its eigenstate. So what is n operations of this vector on its eigenstate? Okay, small ai to the n times ai, right? So I'm going to get, okay, and from 0 to infinity, each one of these things is going to give me an ai. Well, okay, it has to go into the other summation as well. Sorry about that. Okay, ai to the n. Okay, bad notation. This a and that a are obviously different. Okay. Let me just convert this to something like c, because this is obviously, okay, sorry about that, changing the notation, but this is how I define my c, okay, because then I'll get interference with my c's here. Sorry about that. Okay, so Cn ai to the n ai psi. Okay, let's just switch the order of these summations. I am going to get, let's see, n Cn ai to the n and ai psi. Now, what is Cn? Oh, it's f of ai, great. So this term here is f of ai, which gives me I f of ai psi. So the
Sir,
yes.
it should have been AI times another
Yeah,
yes,
okay.
AI times
Yes,
times
okay, thank you. Okay, very good. Okay, so you see what we have started with over here and what we have ended up with. Okay, so this just tells you that if I operate on a kit of my state, okay, an eigenstate of my operator, I'm just going to get that function. Okay, so maybe it's easier to write in terms of math. F operating on A on AI is going to give me f of AI times AI. So the function of an operator also has the same eigenkets as the operator itself. Okay, so remember that these AIs are eigenstates of the operator A. So I had AI equal to AI, right? So these AIs are eigenstates of the operator A. If I have an operator f of A, I still have the same eigenstates, but the eigenvalues now become f of, okay, the same function of those eigenvalues. Okay, so if I had exponential, for example, here, this would be the exponential of the eigenvalues. All right, let's see how this can be useful.
Question.
Sure.
Can f of a have can f of a have eigenstates that aren't eigenstates of a?
Not as far as I can see.
But if, for example, a is not one-to-one, then let's AI and HA.
No. In physics, we have all functions are nice one-to-one, and such thing. We don't have such functions. If we do have such functions, then even the definition becomes a little questionable. Okay, right? Then how do you define the operator? It's not. Yeah. Well, if it's same series, then it's one-to-one. No problem about that. Okay, let's just look at the solution to the Schrödinger equation. Okay. What do I have for the Schrödinger equation? I have I h bar d dt psi equals h psi, right? Now, this just says, okay, let me just make a trivial change. D dt psi is equal to h over I h bar psi. Now I want to solve this equation, and we have been working on this equation for quite some time. But what would happen if I had a simple equation which said the t of something, okay, let's call it, I don't know, g of t, is equal to some a times g of t. If I gave you an equation like this, you would say, okay, that's a very easy equation, right? You would just say that this is equal to g of t is equal to e to the a t, okay, times g of 0. Given the initial condition, that's how I find it. Now let's see if we can try that over here, because if we can get it, then of course this is very nice. If I just tell you that psi of t then is equal to e to the, let me move the I to the top, minus I h over h bar times t psi at time 0. Wouldn't that be nice? Okay, but then we would have to exponentiate h. That's why we need functions of operators. We'll need to exponentiate this h. Let's just check first of all. We have assumed certain things here, so it's best to check whether this is valid. So if I have d psi dt is going to be equal to, d psi dt is going to be equal to d dt of this whole thing. Okay, so what is this? This is 1 minus I h over h bar t, okay, times psi plus 1 over 2 factorial, okay, minus I h over h bar t squared plus, okay, 1 over 3 minus I h over h bar t cubed, okay, dot, 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 everything operating on okay, a psi 0. Okay, let's see if this is a solution of the problem. Well, the first term gives me 0. The second term just takes care of this t. Okay, so let me just factor out a minus I h over h bar. So the first term, when I do the time derivative, is going to be this. So I'll write it as 1. The second term, when I differentiate with respect to t, is going to, cancel this 1 over 2. And I have taken out one factor of minus I h over h bar. So I'll be left with 1 factor of I h over h bar t. If I do the same thing for the third term, this 3 will cancel one of these 3's in the 3 factorial. So it's going to be 1 over 2 factorial. And I'll be left with, a t squared term. So I am going to take out again this thing, and I'll get an I h minus I h over h bar t squared. It's a dot, dot, dot. Psi 0. So indeed, you see, I am going to get the same psi that I had. So I get my original differential equation. d psi dt is equal to minus I h whatever, over h bar times psi of t. So it does check out, which it should, because I have to be careful. When, because I have operators, but I have only operator h here, and h commutes with itself, so I can treat h as if it's an ordinary number or ordinary variable. So because of that, it obeys the same algebra as a t that I have here in the simple equation. I have the same thing here.
But that's because h is time independent, right?
Yes, that's because also h is time independent, because there's no derivative with respect to h that's going on here. So that's very nice. We have found a general solution to the Schrödinger equation. Now, is this compatible with what we did earlier? Let's see. So let's see if that gives us the same results as the previous methodology that we used.
Hocam,
Yes.
can you repeat that part?
Which part?
The two-row equation.
Okay, I'm just looking at d dt of psi, and for psi, I have this. So what I am doing is I am taking this e to the I h t, putting it there, taking psi 0 and putting it there. So that's my right-hand side. And I'll try to see if it's going to give me this equation. When I differentiate it, I should get this right-hand side. So when I differentiate it, indeed, if you look at this term by term, I am going to get e to the minus I h over h bar times the same thing which was our psi. So indeed, I get this equation which says d dt psi is equal to minus I h over h bar times psi t. So I have verified that this is a solution to the general equation. All right, so let's just see. Let me just rewrite that. Psi of t is equal to e to the minus I h t over h bar acting on psi 0. So if someone gives me the initial condition psi 0, in order to find the solution, what was my procedure? What did I do?
Express the mean eigenstates of Hamiltonian.
Okay, express it in terms of eigenstates of the Hamiltonian. Okay, so what are the eigenstates of Hamiltonian? Well, I have these UNs, whatever they are. Okay, En, UN. So let me expand this in terms of the eigenstates of the Hamiltonian. How do I do it?
Insert an identity.
Insert an identity, okay? You see, almost the answer to any question is insert an identity in this game. Okay, so I insert an identity here in terms of the eigenstates of the Hamiltonian. So this psi of t is equal to e to the minus I h t over h bar, and a series n un, that's my identity, acting on psi 0. Okay. Now how do I proceed? I have this function of an operator, right? I have this function of an operator, function of h is an operator, acting on its own eigenstate. So what do I get?
The value
This
of
value.
function and the
Okay, I get the eigenvalue, okay, placed inside the function. Okay, so I'm going to get for each term there, n, e to the minus I, eigenvalue of the Hamiltonian, which is En, t over h bar. So the operator has disappeared. And I have Un, okay, Un psi 0. Okay, so if I now want to find what the wave function is doing, what do? I take the x, okay, inner product with psi of t. That's now going to give me wave function psi of x and t, right? Is going to be equal to n e to the minus I e n t over h bar, okay, x inner with un with psi 0. Okay, so this xun is just the wave function corresponding to un, which we called un of x. You see, we are getting exactly the same thing that we had earlier. These things are the expansion coefficients, Cn, and Cn is just inner product of un with psi 0, so it's going to be un of x, complex conjugate, because it's on the left, psi x 0 dx. So this is what we... where? No.
Oh, no.
Okay, so this is how we found the expansion coefficients. Exactly the same thing. This is the expansion, okay, functions, un of x's. And these are the modification to these coefficients due to time dependence. So we get exactly the same thing. Okay, so in fact, usually you still have to do more or less the same thing. Okay, you cannot run away from evaluating this integral because we are writing it as an inner product, but you have to evaluate it as a number. Okay, then you have to do this integral. But you see how compact the solution can be written like this. Okay, so it enables you to write down the solution very simply, and then you just do standard operations meaning insert an identity and such things, and everything just falls out of it. Okay, so it's a very simple. Okay, so since you have seen this after the our discussion of the Schrödinger method and whatever the differential equation, it may look a little okay, suspicious to you, okay, a little strange to you, but actually it's much more straightforward and direct and easier to handle, okay? You don't, especially in terms of notation, you don't have to write these long integrals and things like that, okay? Everything is very compact. Okay, any questions? Yeah, I'll let this class go, but I'll be here.